How does the tech that runs our world really work? We break it down to its fundamental truths. This is First Principles.
You walk into a pharmacy or a clinic, maybe a converted gymnasium. You sit in a plastic chair. You roll up your sleeve. You feel a cold wipe of alcohol, a quick pinch, and then a Band-Aid is slapped on. You wait 15 minutes, you walk out, and you go on with your life. It is the most mundane medical interaction imaginable. We treat it like checking a box. But if you could shrink yourself down to the size of a molecule and dive into that tiny drop of clear liquid that just entered your muscle, you would see something that looks less like biology and more like an alien technology. We assume that vaccines work the way they always have. We assume we are injecting a dead germ, a piece of the enemy, to warn our bodies of a coming attack. We think of it as a wanted poster. But that is not what happened this time. That clear liquid didn't contain a piece of the virus. It didn't contain the enemy at all. It contained a message, a set of instructions. It was the biological equivalent of a USB drive plugged into the hardware of your arm. So, how does a microscopic strip of code teach a living body to fight a war it hasn't started yet? What simple, elegant rules allowed us to compress decades of medical evolution into a single year? Today, on First Principles, we are hacking the body's code. We are cracking open the black box of the mRNA vaccine. To understand why this technology feels like magic, we have to look at the world before it existed, and we don't have to look back very far. Before 2020, if a new virus emerged, humanity had a playbook, but it was a slow, dusty, and incredibly difficult playbook. It was the playbook of the 20th century, and really, it hadn't changed much since the 18th century. The old way of making a vaccine was essentially farming. You had to identify the virus. Then you had to get your hands on it. You had to grow it. And viruses are picky. They don't grow on trees. They grow inside living cells. For decades, the gold standard for making vaccines, specifically flu vaccines, was chicken eggs. Millions upon millions of fertilized chicken eggs. Imagine the logistics. You have a factory. You have trucks delivering endless crates of eggs. You have technicians carefully injecting a live virus into each egg. You have to wait for the virus to replicate and fill the egg. Then you have to harvest the fluid, purify it, and then kill the virus or weaken it so it can't actually hurt anyone. This is biological manufacturing. It is messy, it is slow, and most importantly, it is risky. If the virus mutates while it is growing in the egg, the vaccine might not match the real-world threat. If you are allergic to eggs, you are out of luck. But the biggest problem was time. It takes months to set up the supply chain. It takes months to grow the virus. It takes months to purify it. When a pandemic hits, it moves at the speed of a jet plane. The old way of making vaccines moved at the speed of a horse and buggy. We were fighting a digital-age fire with a bucket brigade. When the virus that causes COVID-19 emerged, we knew the old way wouldn't be fast enough. We needed something that didn't rely on biology's slow, messy growing cycles. We needed a way to skip the farming and go straight to the instructions. This is where the story shifts from biology to information theory. The black box we are looking at today is mRNA, messenger ribonucleic acid. You have heard the acronym 1,000 times, but let's strip away the jargon and look at what it actually is. Think about your body. You are made of cells, trillions of them, and inside every single one of those cells, there is a control center called the nucleus. Inside that nucleus is your DNA. We all know DNA. It is the double helix. It is the blueprint of you. It contains the instructions for your eye color, your height, your blood type, and every enzyme in your stomach. DNA is the master copy. It is the reference library of the universe. It is incredibly precious. Because it is so precious, the cell has a very strict rule. The DNA never leaves the nucleus. It stays in the vault. But here is the problem. The actual work of the cell, building proteins, repairing tissues, creating energy, happens outside the nucleus, in the main body of the cell, the cytoplasm. This is the factory floor. So you have a situation where the blueprints are locked in the manager's office, but the workers are on the factory floor. How do you get the instructions to the workers without risking the master blueprints? You make a copy, a cheap, disposable, temporary copy. This is mRNA. When your body needs to build a protein, let's say insulin, the DNA opens up just a tiny bit at the specific page for insulin. An enzyme reads that page and transcribes it into a single strand of RNA. That strand, that messenger, floats out of the nucleus and goes to the factory floor. Waiting on the factory floor are the machines. They are called ribosomes. If you remember nothing else from high school biology, remember the ribosome. It is the 3D printer of the body. It grabs that strand of mRNA and reads it. The mRNA says, put this molecule here, then that one there, then fold it like this. The ribosome follows the instructions and spits out a protein. Once the protein is made, the mRNA strip is shredded. It is recycled. It is gone. It is a Snapchat message. It is read once or twice, and then it deletes itself. This system, DNA makes RNA, RNA makes protein, is the central dogma of biology. It is the flow of information that makes life possible. It has been happening in every living thing on Earth for billions of years. Now, here is the record scratch. Here is the question that changed everything. If the ribosome is just a machine, and if it just blindly follows whatever instructions you feed it, what if we wrote our own instructions? What if, instead of waiting for the DNA to release a message, we synthesized a message in a lab and slipped it into the factory? This is the core concept of the mRNA vaccine. It is not medicine in the traditional sense. It is code injection. We are hijacking the body's existing 3D printers to manufacture a drug inside of us, rather than in a vat in a factory. But hold on. If the concept is that simple, just write a note and slip it to the ribosome, why didn't we do this 50 years ago? Why did it take a global crisis to bring this to the forefront? This is where we meet the pioneers, and where we encounter the massive, seemingly impossible hurdle that kept this technology in the dark for decades. Enter Katalin Karikó. She is a Hungarian biochemist who became obsessed with this idea in the 1980s. She looked at this system and saw the potential. She thought, if we can give the body the instructions to heal itself, we can fix anything. If you have anemia and need more red blood cells, we can just inject the mRNA for the hormone that stimulates red blood cell production. If you have a heart attack, we can inject mRNA that tells the heart to repair its tissue. It sounds perfect, but there was a problem, a big one. Our bodies are smart. They have spent millions of years fighting off invaders, and many viruses, specifically the bad ones, use RNA to replicate, so our immune system has evolved a hair-trigger sensitivity to foreign RNA. When Karikó and her colleagues tried to inject synthetic mRNA into mice in the early days, it didn't work. The mice didn't just make the protein. They got sick. They got massive inflammation. The immune system saw this foreign genetic material and freaked out. It thought the mouse was under viral attack, so it sent in the heavy artillery and destroyed the mRNA before it could ever reach the ribosome. This was the wall. You couldn't use mRNA as a therapy if the body destroyed it on site. For years, Kariko was demoted. She lost funding. She was told it was a dead end. The scientific consensus was that mRNA was too unstable and too immunogenic, too provoking to the immune system to ever work as a drug. But she kept going, and in the mid-2000s, along with her colleague Drew Weissman, she found the hack. They realized that our own bodies make mRNA all the time, and our immune system doesn't attack our own mRNA. Why? What is the difference between my mRNA and the synthetic stuff made in the lab? It turned out to be a chemical signature. One of the building blocks of RNA is a molecule called uridine. In foreign RNA, the uridine stands out like a sore thumb. It triggers the alarm. But in our own bodies, that uridine is often chemically modified. It wears a disguise. Kariko and Weissman discovered that if they swapped out the regular uridine in their synthetic mRNA for a modified version, something called pseudouridine, it became invisible. The immune system didn't see it as a threat. It let it pass. This was the breakthrough. Suddenly, they could slip the message past the guards. They could get the instructions to the factory floor without burning down the factory. So we have the concept, we have the history. Now let's look at the specific black box of the COVID-19 vaccine. Let's deconstruct exactly what happens, step by step, when that needle goes into your arm. We start with the enemy, SARS-CoV-2. The virus looks like a ball covered in spikes. Those spikes are famous. They are the red protrusions you see on every news graphic. Those spikes are the key. They are the battering ram the virus uses to break into your cells. Without the spike, the virus is harmless. It can't get in. In the old way of making vaccines, we would have grown the whole virus, killed it, and injected the corpse. Your immune system would bump into this dead virus, study the spikes, and learn to recognize them. The mRNA approach is cleaner. Scientists in a lab looked at the genetic code of the virus. They found the specific section of code that describes the spike, just the spike, not the rest of the virus, just the instructions for the battering ram. They copied that code. They turned it into a strand of mRNA, and that is what is in the vial. When the vaccine enters your arm, those mRNA strands float up to your muscle cells. They slip inside the cell wall. They find the ribosomes. The ribosome grabs the mRNA and starts reading. It says, "Okay, I need to build this protein." It doesn't know it's building a piece of a virus. It's just following orders. It strings together amino acids and builds the spike protein. Once the spike is built, the cell pushes it to the surface. Imagine your muscle cell suddenly holding up a sign. It is displaying the spike protein on its outer wall. Now the immune system comes patrolling. It sees your muscle cell. It sees this weird spike sticking out of it. It knows that spike doesn't belong there. It looks foreign. The alarm goes off. Your immune system swarms the area. B cells come in and study the shape of the spike. They start designing antibodies, custom-made weapons that are perfectly shaped to latch onto that specific spike and gum it up. T cells come in and learn to recognize cells that are infected with anything bearing that spike. This is the training run. Your body is fighting a war simulation. It is fighting a ghost. There is no virus, only the spike. But the lesson is learned. Your immune system files away the blueprints for the antibodies in its memory cells. Then the mRNA disintegrates. The cells break down the spikes they made. The battlefield clears. 2 weeks later, or 6 months later, the real virus enters your nose. It is covered in those same spikes. But this time, your body isn't surprised. It recognizes the shape instantly. The memory cells wake up. They flood your blood with antibodies. The antibodies snap onto the spikes of the virus before it can even touch a cell. The virus is neutralized. You might not even know you were exposed. That is the elegance of the system. We didn't give you the fish. We taught your body how to fish. But wait, I promised you a deep dive. I promised you the first principles view. And if we stopped here, we would be missing the most critical piece of engineering in the entire puzzle. We talked about the message. We talked about the code. But we haven't talked about the envelope. If you took naked mRNA, just the genetic strands, and injected them into your arm, nothing would happen. Absolutely nothing. Why? Because your body is a hostile environment for loose genetic material. Your blood and tissues are full of enzymes specifically designed to tear RNA apart. It's a defense mechanism. Ancient viruses used RNA, so we have enzymes that act like shredders, patrolling our fluids, looking for stray code to destroy. If you inject naked mRNA, those shredders would eat it up in seconds. It would never reach the inside of a cell. And even if it survived the shredders, mRNA is a large, negatively charged molecule. The membrane of your cells is a layer of fat. Fat repels the large, charged mRNA. It would just bounce off the cell wall. It couldn't get in. So, the brilliant code that Kariko and Weissman developed, it's useless if you can't deliver it. This brings us to Part E, the unseen giant, the unsung hero of the pandemic. The lipid nanoparticle. This is the aha moment. The reason these vaccines work is not just because of the genetic code, but because of a microscopic ball of fat. Scientists had to engineer a delivery vehicle. They needed a capsule that could do 3 things. First, it had to protect the fragile mRNA from the shredders in the blood. Second, it had to sneak past the immune system's radar. And third, and this is the hardest part, it had to merge with the cell wall and release the payload inside. Think of the cell like a fortress with a moat of oil. You are trying to throw a water balloon into the fortress. It just bounces off. So, engineers created the lipid nanoparticle, or LNP. Lipid means fat, nano means tiny. These aren't just grease balls. They are highly engineered structures. They use 4 specific types of fat molecules. One provides structure. One prevents the particles from clumping together. One mimics the cell wall. But the 4th lipid is the magic trick. It is an ionizable lipid. Here is how it works. When the LNP is floating in the vial or in your blood, this lipid has a neutral charge. It is quiet. It holds the mRNA tight and protects it. But the moment the LNP touches a cell, the cell tries to eat it. The cell pulls it inside in a little pocket called an endosome. The environment inside that pocket is acidic. When the pH drops, that ionizable lipid suddenly changes shape and charge. It becomes positively charged. Remember, the cell wall is negatively charged. Positive attracts negative. This sudden shift in charge causes the fat bubble to fuse with the wall of the pocket, tearing it open. This is the escape moment. The LNP breaks open, and the mRNA is released directly into the cytoplasm, safe and sound, right next to the ribosomes. Without this specific high-tech fat molecule, that changes its personality based on acidity, the mRNA vaccines would not exist. We would still be waiting for chicken eggs. This deconstruction reveals something profound about the nature of this technology. We often hear people worried that the vaccine changes their DNA. We hear the fear that it modifies us. But when you look at it from first principles, you see the opposite. It is remarkably transient. The mRNA doesn't enter the nucleus. It physically cannot. It lacks the password, a specific chemical signal called a nuclear localization sequence that is required to enter the nucleus. It bounces off the nuclear door. Furthermore, mRNA is incredibly fragile. It is designed by nature to degrade. That is why the vaccines have to be kept at ultra-cold temperatures. The moment they warm up, they start to fall apart. Once inside your body, the message lasts for a day or two, maybe a little longer, and then it is gone. The only thing that remains is the memory. It is like showing a blueprint to a builder, letting them memorize it, and then burning the paper. The builder remembers how to build the wall, but the paper is ash. So, what have we actually learned? We started with a pinch in the arm. We found that the liquid was not a dead virus, but a set of instructions. We learned that the body is a factory, and the ribosome is a 3D printer waiting for orders. We learned that the pioneers had to teach the code to wear a disguise to get past the immune system. And we learned that the whole operation depends on a Trojan horse made of high-tech fat that melts its way into the cell. This matters because it is not just about COVID-19. This is a platform change. We have moved from the analog age of vaccines, growing biological material in eggs, to the digital age. If a new virus appears tomorrow, we don't need a new factory. We don't need to figure out how to grow it. We just need its sequence. We can email the sequence to a lab. They can type it into the synthesizer. They can print the mRNA. They can wrap it in the same lipid nanoparticles we already have. We can have a new vaccine design in days. And it goes beyond viruses. Scientists are now looking at mRNA to treat cancer. Imagine taking a biopsy of a tumor, finding the unique proteins on that specific cancer, and printing an mRNA vaccine that teaches the patient's body to hunt down that specific tumor. We are no longer just passive observers of our biology. We have learned to speak the language. We have found the command line. We used to have to fight nature with nature. Now we can fight it with information. And that simple shift from the physical to the informational is the principle that will define the next century of human health.
You've been listening to First Principles. Until next time, stay curious.